Hi everyone, thanks for coming out tonight to listen to me talk about science data centers. I'm Alex and I work in the data systems group here at LASP, as many of you know, because some of my coworkers are here tonight too. And so yeah, I spend pretty much all of my time thinking about science data centers. That is what I do, and so that's why I'm standing here tonight. So we're going to talk about how we turn bits that come back from the spacecraft into actual science results. But first of all, let's just think for a minute. What is a data center? So science data centers, what does that mean? What do we think of when we think of a data center? I'm going to use this clicker and see if it works. Ah, look at that. So maybe you think of, giant racks of computers and lots of blinky lights and cables, and that's a data center. Sure, yes, that is an important part of a data center. Maybe you think about people standing around entering numbers and plugging in cables. These are some of my coworkers. Maybe that's a data center too. That's another part. Maybe you think about really exciting giant lists of file names. That is part of our data center because you got to know where your data is. Maybe you think about incomprehensible streams of numbers. All of these things make up a data center, except maybe not the matrix because that's kind of creepy. So in our data centers here, we do science processing, science data processing. So we transform the data. We store the data. We make sure that it's securely stored from now and into the future. We distribute it. We make it available to people around the world. And we archive the data, which is a little different from storage. When you want to archive something, you have to think about storing it in the long term and making sure it's accurately documented and stored for a very long time and still accessible. So around here at LASP, we manage a whole lot of different kinds of data centers, different data centers and different kinds of data centers. We have data centers for missions. So we have individual spacecraft missions like Maven, which is top here because it's very close to my heart. It's my first big project. Maven is a mission to Mars, and we have all of the Maven science data stored here at LASP. We also manage the MMS mission data center. MMS is orbiting the Earth right now, 4 different spacecraft measuring the Earth's magnetic field and its interactions. The SOURCE spacecraft, SOURCE is a solar observing spacecraft that's been up for years and years and years, and we have all of its data here. We also have data from CubeSats. CubeSats are these little bitty satellites, like really little bitty satellites that we send up to do science data. But the data they collect, they don't collect a whole lot of data, but what they do have is important, and so we store it all here. And we have missions like Clario. Clario is in development, and so we're going to have the mission data processing here, but it's not launched yet. We also have individual instrument data centers, so not entire missions, but just one instrument on a spacecraft. And so we have all of these alphabet soup. SDO Eve is a solar observing instrument. AIM-SIPS looks at clouds and the high atmosphere of Earth. Galileo, which some of you may remember from quite a while ago. Again, we have Europa. SUDA is an instrument that's in development right now. It hasn't launched yet. It's going to be launching in 2022 to go to one of the moons of Jupiter, which is really exciting. And we have many more instrument data centers. We also have collections of data that come from many different missions or different instruments, but that have something in common. So LISIRD, which is a great acronym, it stands for LASP Interactive Solar Irradiance Data Center. And yes, we use a little lizard as the icon for the data center. LISIRD is a solar irradiance collection, but it comes from many different sources and different instruments. And so we put it all together in one collection so that people can look at the data from different instruments that measure similar things. And then I put this under Other because it's a little different. The Emirates Mars mission, the data center for the entire mission, is not going to be located here. It's going to be located in the United Arab Emirates, but we're consulting with them on how to build and maintain their data center because we have this expertise here on how to do this. And so in addition to running our own data centers, we're starting to consult with other people on how to run them. So that's the kind of thing we have here. Lots of different data centers, different varieties. And so tonight, we're going to talk about a few things. We're going to talk about how we get data from the spacecraft down to the ground and here. And then what do we do with it? How do we transform it from the bits that come down from the spacecraft into something that we can actually use and look at. How do we store that data once we have it? How do we keep it safe, keep it from evaporating when your hard drive crashes? And how do we keep it secure? And then also, in addition to keeping it secure, how do we get it to the people who need the data? So first, how do we get the data back from space? How does this happen? So I'm just going to talk about one of the main ways that we get data back from spacecraft. And some of you have probably heard all about this and know quite a bit about it. But one of the main ways that we get data back from our distant spacecraft, and especially our science spacecraft, is the Deep Space Network, which we call the DSN because we love our acronyms in this business. So the Deep Space Network is a set of 3 different installations around the world. So there's one in Madrid in Spain, one in Goldstone, California, and one in Canberra, Australia. And so each of these installations has all of these great big receivers that listen for signals from space. And so they're all scheduled very carefully, of course. And you can't see Madrid because Madrid wasn't doing much at this time, and so I cut off the top of it when I took the screenshot. But you can see that each of these receivers has a spacecraft associated with it, a little abbreviation, which I know is hard to read in the back. But one thing you can see right here is this wave is coming from Kepler, K-E-P-L. Here's Kepler over here. Kepler is currently orbiting the sun. It's not orbiting the Earth. It's 20 light minutes away. It's a really long way from us right now. But Kepler was sending back data at the time that I took the screenshot. And the data was coming back into Goldstone receiver and coming across some wires and ending up in the Mach across the hall, like right there across the hall. So it was kind of fun to just take this picture and say, wow, there's the signal coming back from space and it's going right there. And I can see the people sitting in there working on Kepler data. You can also see down here that Canberra was looking at different things. Mars Odyssey, Maven, Mars Express, and Mars Reconnaissance Orbiter. We're all talking to Canberra. And OSIRIS-REx is out there too, but it wasn't sending back signal at that point. So the Deep Space Network is great for listening to spacecraft and sending signals out to spacecraft in deep space, orbiting other planets, rovers. Well, rovers do something slightly different. But this is how we listen to our very far away missions that are sending back a lot of science data, because you can also get a lot of data down through these big receivers. Notice also, though, that I have MMS up here, because MMS is orbiting Earth, so it's not that far away, really. I mean, it's still in Earth orbit, which is a lot closer than, say, Mars. But it sends back a lot of data, and so we need to use the DSN to listen to MMS as well. So we're getting our data back from space, and that's great. We love that. We're getting data from our telescopes. But there are sometimes problems with this data. What happens? So sometimes we have a data stream coming back, and you have your string of ones and zeros. And sometimes you just have a big gap in the middle of it. Dropped out, right? We're missing some data. Sometimes you get your data back, and you're missing every other chunk of data. And so these kinds of glitches and gaps cause problems for the scientists, obviously, because you want all of your data. What causes them? A couple of the causes. One major one is space weather. And so space weather is when the sun throws off a whole lot of charged particles, and it interferes with your transmission. And frankly, you just lose data. This is a problem for lots of different things. Obviously, communications on the ground, aircraft, all of these things that need to communicate can have glitches in their communications caused by space weather. And so what do? We put up more spacecraft to look at the space weather. So I think it's just kind of cute that we have satellites that are monitoring space weather that can cause problems for other spacecraft. So we have spacecraft taking care of spacecraft, which is nice. So space weather is a big problem. But another problem that we encounter, remember I said that one of the DSN receivers was in Spain. Well, in Spain, sometimes it rains. And because we have all seen My Fair Lady and we like to sing, yes, the rain in Spain stays mainly in the plane except when it also messes up your transmissions. And so, yes, just like you have your DirecTV dish on your roof and sometimes you get a thunderstorm and you lose the football game, also the weather here on Earth can affect these giant telescopes and cause gaps and dropouts in transmissions. And this is a pretty common problem. And so even if it's rain in Australia rather than rain in Spain, we sometimes just refer to rain in Spain because it rhymes. Sometimes we don't know what causes the problems, but we still lose data. And so one thing that we have to think about is when we lose data, what do we do next? Can we go back and get it? So sometimes you can tell that, you know, maybe there was some space weather incident that caused you to lose a little bit of data. Well, you have to look at what you have around the gap and say, is this really important? Do I need to go back and fetch it again? Every spacecraft is a little bit different in the way it stores data. Some spacecraft have a ton of onboard storage, and they can keep like 2 weeks worth of data at any given time. And so you can, if you're really lucky, you can request more time on the Deep Space Network. That's pretty rare because it's pretty tightly scheduled. But you can also go back and say, well, I have another connection to the spacecraft later this week scheduled. Do I go back and get the data I'm missing, or do I get the new stuff? And so this is a real judgment call that our scientists have to make. And so we need to have people who know the science and who know what they're looking for in the data, monitoring what we're getting back so that they can make that judgment call and say, well, I think that what we missed was actually really important, and so I want to get more of it down. I want to go try again and ask for the spacecraft to send that data back. Or they can say, well, you know, what's coming next is more important, so we're not going to worry about the old stuff, we're just going to worry about the new stuff and get that back now. So that's the sort of thing that the scientists have to consider when they're looking at gaps and the need for retransmits in our data. So then what happens? Whoops, I skipped one. How do we turn those actual bits that we get back from the spacecraft into something that we can use? Because the stuff that the spacecraft sends back, trust me, is not readable by normal human beings. Okay, I'm going to introduce a concept for you all to think about. There will not be a quiz later, I promise. We're going to talk about data levels. And this is something that we talk about all the time. Every mission, data levels. So the stuff that you get back from the spacecraft is the raw telemetry. That's just what we call it. It's a whole lot of zeros and ones. It's just bits that we get from the spacecraft. Bing, 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 bing. A row of bits coming back. Then we unpack that a little bit and we turn it into more binary data, but we call it level 0 data. It's a little bit more organized. There's, you know, we take off some of the wrappers and we call it level 0. And then we move up to level 1, and you can see actual numbers, not just ones and zeros, stuff that you might recognize, except it doesn't really look very meaningful. I mean, that's like 518032134.600. I have no idea what that means, right? And so we take the level 1 and then we turn it into level 2, and level 2 is where the magic happens. This is the science stuff, the good stuff. There are also level 3 and level 4, but that's generally generated by the scientists, not by us in data systems, and so I'm not going to talk about it tonight. Level 2, you go from incomprehensible numbers to slightly more comprehensible numbers. This is 2017, and we all know what that means. That actually means this year, right? 2017, that's a real date. So sometimes level 2 products are just tables of numbers like this. But sometimes they're actually really pretty plots too. I mean, they don't always have to be beautiful rainbowy plots. Sometimes they're just boring black and white. But you know, this is actually timestamp data. So this is from Maven, and this is 2017, August 14th. And so you have an altitude plot right here. So this is a level 2 product. This is also a level 2 product that I pulled off the internet. This comes from the AIM spacecraft, which is another one that we operate here. And you can see this is actually a map of the North Pole of the Earth, I believe. And over here is some data. And so this isn't a plot, a line plot. It's not numbers. It's actual data plotted on a map, so you can see where the magic was happening, where the science is. And so keep in mind these data levels, because this is how we talk about transforming data. We talk about going from the raw telemetry all the way up to level 2. And that's what we do with data. So I'm going to walk through the processing steps a little bit and give you an overview of what happens at each step. Okay, first, raw telemetry going to level 0. Now, this is not my wheelhouse. I usually work higher up in the processing end of things, and so if you have any complicated questions, don't ask me, ask a couple of these people in the audience who know it better than I do. So, when you get the data from the spacecraft, you have this string of 1s and 0s, and you have to unpack it. And one way to think about it is that you have a package from the spacecraft, and you open it up, and there's a shipping manifest, and there's another box. And then you open that up, and there's another shipping manifest and another box. And so you keep having to unpack the layers until you get to the stuff that you really want. But we have to put a lot of organization and a lot of labeling and IDs and stuff like that into the data, because if we lose a bit here or there, we want to still know what we're looking at. So we have a lot of redundancy built into this system. And so I'm going to talk about one chunk of spacecraft data, spacecraft telemetry, and then bring it down to the science data. So we have a big chunk of spacecraft telemetry, right? And we're going to break it up into a section called a frame. And then there's another frame and another frame. There are lots of frames. And then within each of these frames, you have header things like spacecraft ID. Which spacecraft did this data come from? You want to know that. You want to know what time the data was collected. You're going to get it in spacecraft time rather than Earth time, but that's good too. And there are a lot of other things, identifying information about the condition of the spacecraft when the data came in. So you get through some of the frame information, the wrapper, and you unwrap it, and then you get a packet. You get lots of packets, but we're just going to talk about one. Within the packet, again, there's another header. There's going to be version numbers about what kind of software, what version of software produced the packet, produced the data. You're going to have a packet type, packet data length. So the spacecraft is telling you, hey, here comes some data. It's going to be this long, and it's going to be this kind of data. So this is what to expect. Okay, here's the data. So it tells you what to expect, and then it gives you the data. And then you get data. Yay! Along with the data, you get a timestamp again. You get something called a checksum. Checksums are something we use on Earth on the internet all the time. It's a way of telling when a file is sent or a piece of data is sent, if the thing that was sent is the same as the thing that was received. So it's just a way to know if anything dropped out in the middle. So you have a checksum, and then you have data. Woo, we're finally at data. Oh wait, there's two kinds of data. There's housekeeping data and science data. You know what science data is. That's the actual measurements that we're talking about. Housekeeping data is everything else that you might need to know about the spacecraft and the instrument that's not science data. Like you want to know what temperature your instrument was at when the data was collected. Because that kind of information tells you, first of all, is the instrument safe and healthy? Is it a happy instrument? Is it working correctly? Or is there something wrong? And so we monitor housekeeping for that. But we also want to know, that information because that tells you something about how the data was collected. So if the instrument was a little bit warmer, a little bit colder, or a little bit more charged when the data was taken, that will affect your readings, and you want to be able to take that information back out of your science data. And so we wrap this all up into the telemetry, but then we have to unpack it when it gets to Earth, and we call it level 0. So then what do we do? Okay, so we go from level 0 to level 1, and honestly, there's not a whole lot to say at this point. This is where we transform the binary data into something that's human readable. And so we use processing software that does this. We write it in Python, we write it in C, C++, sometimes even Fortran used to be in use, sometimes Fortran is still in use, and we're trying to fix that, but sometimes you use what you got, right? And so this takes you from binary, which you can't really look at, to numbers, columns of numbers, But these numbers are still in the form that the spacecraft sent them back. So like this number, this column right here, you can see is counting. You probably can't see because it's kind of small. But it's going, 518032125, 26, 27, 28. This is a spacecraft counter, right? This is a clock, but it's in the spacecraft's time frame. It's not anything that we can really recognize. And so that's our level 1. It's an intermediate step. It still has all of the numbers in the format that the spacecraft sent them back. So then what do we do? Then we have to turn those numbers into something meaningful, something we understand. And so again, we have software. Again, Python, C, whatever. And we write this software, this processing software, to transform from level 1 to level 2. And the critical things that we do here are applying calibrations and corrections and geometry. And also time corrections. You can see we're going from the counter to 2017, which is great. But that's sort of wrapped up in the geometry and time transformations. And so I'll talk about those together in just a minute. So that's going from level 1 to level 2. We apply calibrations and corrections and geometry and time corrections and changes. But what does that mean? All right. So here's a kind of correction that we do, especially for image data, but this is a good way to think about it because you're used to looking at images. So say you have a camera and it's got, lots of pixels in your little CCD, and you want to know, do all of those pixels respond to light in the same way? Is it even? Is it flat? So you can take a picture of a white piece of paper, and you can look at your picture and you can say, well, it's a little darker here than it is over there. And so that's how you know that your camera is responding the same way all the way across the CCD chip that's taking the pictures. And this is actually what we do with ground-based telescopes. We take something called flat fields. It's a flat white field. We just take a picture of, and really is a white piece of paper at some telescopes. You just mount it on a frame and take a picture of it, and that's your flat field. But this is the flat field for a very big, exciting telescope, the Hubble Space Telescope. And so you can see there's some variation between these two detectors. There's a bad row right here, bad column. And you can see there's this like weird wonky wedge shape right here where it's brighter. So if you're taking pictures on Earth with a nice camera, you don't really care if there's like a tiny variation from one side of the CCD to another. But when you're taking pictures in space of stars and galaxies that are very dim and distant, you want to be able to say, look, this pixel should be a little bit brighter, a little bit darker when you take your image. You have to know how your camera is responding to the things you're trying to take a picture of and what's just an effect of the detector. And so you take these flat fields so that you can then subtract them off of your image or divide through your image and remove the effects that just come from the camera itself and end up with something that's really an accurate scientific observation of what you're trying to take a picture of. So that's from Hubble. This one is a flat field from the ACES instrument on the Chandra X-ray telescope, which I worked on a very long time ago. And you can see over here, there's some really serious detector artifacts going on. So you want to know what those are so you can subtract them off, again, when you take your images. Because if you take a picture with this and you have this sitting there, you're going to be like, whoa, what is that? Is that like a galaxy? Is that some quasar? No, it's just a problem with your camera. So you have to know that before you start taking your images. But there's a trick. Remember I said we can take a picture of a white piece of paper. This is an X-ray telescope. You can't take a picture of a piece of paper. You have to have something that puts out X-rays. So how do we calibrate instruments that don't work in the optical? What do we do? Well, what we do is we go find a source of photons that are not in the optical. So this is something called ground-based pre-launch calibration of an instrument that we built here at LASP. You can tell we built it here because it has a little buffalo built in. We put a little buff on everything that we built. And so this is the EXIS instrument, Extreme Ultraviolet and X-ray Irradiance Sensors. They're looking at the sun from satellites that are orbiting the Earth, so observing the sun. But we had to go find a source of ultraviolet radiation that we could fire at this detector and figure out how it reacted when you fire very accurate ultraviolet photons at it. So we take it to a facility in Maryland called SURF, the Synchrotron Ultraviolet Radiation Facility, and it's a synchrotron. So they spin electrons around in a big ring, and it puts off very precisely calibrated ultraviolet radiation. And you can just stick your detector into the beam right there and get a very carefully, very accurate, very carefully measured stream of photons. And if your detector is looking at this and says, well, I just registered that that is 600 nanometer photons. Okay, that's great. But actually, you know that the ones that it was supposed to be getting were 630 nanometers. So you know that maybe it's a tiny bit off. The measurements are a little bit off. That's always going to happen. Every instrument has to be calibrated. You have to be able to tell what the reading corresponds to in reality. And so we take these measurements on Earth so that when we send the instrument up into space and we get a reading back, we know just how much we have to adjust it in the processing. And that is the correction that we have to apply, the calibration and correction that we have to apply to get our data right. All right, so I mentioned geometry. So geometry you have to apply because when you get data back, sometimes you don't know exactly where it was taken, or you do, but you have to figure that out very carefully. So say you take a picture of Mars. You've got a picture that comes back, but you don't know if that picture looking down at the surface of Mars is a picture of this much of Mars, or the size of this table, or the size of this room. How big of an area on Mars does your picture cover? So we use geometry calculations to figure out how much space you're taking a picture of, but also we need to know what direction your instrument was looking. Was it looking straight down at the surface? Was it looking off at an angle? So maybe you see some mountains, you see a little bit of the surface, a little atmosphere. Was it looking off at the edge of the planet and just seeing the edge and more of the atmosphere? And in order to have a really accurate description of all of this, you need to apply geometry corrections. You can also see that you know where the spacecraft is pointed, right? This is the Cassini spacecraft, obviously, by Cassini, orbiting Saturn. It was a wonderful spacecraft while it lasted. So you have to know how the spacecraft was oriented in space, but you also need to know how the instrument was oriented, because not all instruments are mounted fixed to the spacecraft. Sometimes they can look around. So instead of turning your entire spacecraft to take a picture, you can just turn the instrument and take a picture, which is a lot more efficient in some ways, but has its drawbacks as well. So you have to know where the spacecraft was pointed, where the instrument was pointed, how big the field of vision of the instrument is, and you apply all of that and you finally get an accurate picture of where and when the data was collected, how exactly that data translates to a point on the surface or off in space. So to do this, we use some fun files that we get from NASA and from spacecraft navigation teams, and they're called SPICE files, which I just think is a great acronym, and I won't even tell you what it means because it's kind of meaningless at this point. But we apply these standard files called SPICE kernels to our data, and what I think is cool is that there's a SPICE kernel description for pretty much everything in the solar system. There's one for the Earth, there's one for the Moon, there's one for every spacecraft we've got out there. There's ones for the moons of Mars, so that if your spacecraft is going around Mars, you cannot crash into the moons of Mars, which we had to correct for recently, so we didn't crash into Phobos, I believe. Yeah, it's good not to, you've got a many millions-dollar spacecraft, not to run into the moon by accident. And so these files are really useful for us to do our corrections, but they're also important for navigation and for mission design. So that's geometry. There are also SPICE kernels that tell you about spacecraft time. and spacecraft clock, and leap seconds. We all love leap seconds. They're a huge pain in the neck. But that's also how we do our time conversions. So when I said we were going from a spacecraft counter that just goes 1, 2, 3 to June 23rd, 1975, that is a spice kernel translation as well. And so once we've done all of this, we've got our telemetry back, we've gone to level 0 and 1, 2, 3 even. What does the spacecraft data, what does the science data look like when we're done? What kind of formats do we have? I'm just putting this up here because I know that some people are total data nerds like me and like to know what kind of actual data we're getting back, what kind of formats. So like I said, we do get ASCII files, just columns of text, or sometimes comma delimited columns of text with numbers. And these are super useful. They may not look very exciting, but they're really important to the scientists. And this is what we need to put out with our data processing. So sometimes you just want files with lots of data in it. Sometimes we get these line plots and spectrograms like this. Like I said, these are also super useful. You can see how the altitude of the spacecraft is changing, and then also how the magnetic field varies. So maybe the magnetic field variation corresponds with some difference in altitude. Sometimes you want to make images, and sometimes your images aren't pictures of the surface. Sometimes they're images of something else. This is a spectrum, or several spectra, of the plasma torus generated by the moon Io as it goes around Jupiter, taken by the Cassini spacecraft as it flew past Jupiter on the way to Saturn many years ago. And so this is a spectrum. You can see wavelength on one side, distance from Jupiter up here, and you can just see the shape of the plasma torus right here, over and over. There's that ring. And so you can use this to figure out what the composition of the plasma is around Jupiter, which is really cool. And then sometimes our data gets overlaid on a map. We do this for Earth. We also do this for Mars and the Moon, and sometimes even other bodies in the solar system, though we don't have as many maps for them. It's useful to know where on Earth or on another body your data is, and so we produce that kind of level 2 data product as well. And so for those of you who are real nerds, we have the alphabet soup down here of all the different kinds of data formats that we use. CDF, HDF, JPEG. Sometimes we make JPEG images just like you see on your browser. We also put data into databases sometimes. We don't just produce single files over and over. Sometimes it's very useful to have a very large complex data set in a database so that you can search and query that data. All right, how do we distribute and store the data once we have it? So we've done all this processing. What do we do next? We got to hang on to it. We got to keep it safe. So we're going to talk about data storage. And you can see we have some high quality data storage up here. We got punch cards. Now, you all think this is hilarious, and I am making a joke, but let me tell you about the time several years ago when we realized that we had punch cards here with Mariner data, and that we had that data and it was on punch cards, and we didn't have punch card reader anymore. And it was not the 70s, it was the 90s or maybe the 2000s. And we said, we want this data, we can't just throw it away. I mean, we sent a spacecraft into space with lots of money, and we want to keep this data. So Chris is smiling because he was in charge of this project. Yes, we had to go find a guy who had a punch card reader in his garage, no joke, and send him a check. Actually, I think we may have had to send him cash, and the punch cards, and say, would you please read our punch cards for us? And he did, and we ended up with, some nice hard drives, or maybe just one, because it wasn't a whole lot of data, a big stack of punch cards fit on a thumb drive. And we ended up with our Mariner data. We finally got it back, and we put it onto, actual modern storage, and then we put it onto Google Mars. And so you can look at this Mariner data and, from ancient technology, from punch cards to Google, to something very modern. And so that's the kind of thing that is important to think about. I mean, I don't know about the rest of you, but I have cassette tapes still and CDs sitting around my house, and I have one CD player and it's in my car. And so I have to find a way to convert this data into something modern and not forget about it. You can't just forget that you have a rack of tapes sitting outside your grad student's office, which happens, and not have a way to read those tapes in anymore. You need to know where your data is, and you need to be able to transform it into something that is readable and make sure you keep on top of that over the years. So nowadays, most of our data is in these nice big racks of data storage with flashy lights and wires. And that picture was taken right across the hall, just down the hall there. And so we have modern server technology, and we store our data on backed up, redundant hardware. We're also moving toward using the cloud more. So we know that Amazon has some pretty great services available for us that we can store data there, and it will be safe and secure and maintained. We just have to pay them a little bit of money. And so we're starting to use Amazon for backups, but also for some of our processing. So we're working locally, but we're also working more in the cloud. But we don't just get the data and leave it here. I mean, we have to have somebody reading and using the data. We want to make it available to people. Because in fact, all of this data belongs to all of you. These are NASA missions. They are funded with taxpayer money. That data is public property. And so the data, NASA is very good about making sure that we release our science data in a timely fashion. There is a little bit of a caveat there in that you don't want to release it as soon as it comes down from the spacecraft, because honestly there might be things you don't understand about it yet. There might be incorrect calibrations or things that you haven't adjusted correctly yet. There might be, God forbid, bugs in our processing software. That never happens, actually. No, everything is always perfect from the beginning. But you want to have a little bit of time to look at the data and make sure you understand what's going on with it, so that your processing is all correct and running properly before you release it to the world. And usually that's just a few months. And so once we do that, we put our data out on the internet for everybody. And so these are a couple screenshots from our MMS Science Data Center website and our Maven Science Data Center website. These are some of our magnetometer files, and they're out there. You can go look at them. You can see all the magnetometer data that you want from Mars, which I know you're all super excited about. But we also put up things, not just lists of files. We put up things like this that are quick look plots, so that you can go and say, hey, what was the spacecraft doing on November 13th? What was the data like on November 13th? Okay, looks good. We got a lot of data. But you can go back through day by day and say, wow, there's some data missing there, or there was some big interesting spike. And so this is a good way to browse through what was going on with the spacecraft on any given day. We also have some search interfaces so that you can say, I want all the data from November, from MMS1, and there are more options down here that I cut off. But then it gives you a list of files that comes back and says, hey, this is exactly what you wanted. Sometimes it says, this is 5 gigabytes of what you wanted. Maybe you want to reduce that search a little bit before you download. But sometimes, you get a reasonable amount of data. So we distribute data to the scientists and to the general public through our websites. We also sometimes put data in these collections, like this lizard collection that I mentioned earlier. So we'll put data together. If it has a common theme, we'll collect all of our solar data in one place. But then we also have these requirements to send data to NASA. NASA says that any planetary mission that goes into space on NASA money has to send their data to the Planetary Data System Archive. And that's because these are government documents. This data is government documents, and it has to be stored for the same time as any other government document, which is to say 200 years. And if you thought we had a problem with punch cards, think about storing data for 200 years and how much things are going to change over that amount of time. So we let the PDS worry about that. That's fortunately not our problem. But we do send them our data. And they're actually very good about things like checking and making sure that everything we send them is complete, that it's well documented, that it's organized in the way that I expect it to be organized. And then everyone can go to the PDS or to the Space Physics Data Facility for space physics data and get data from multiple different missions. So you can go to the PDS and say, I want all the Mars data. And you can see every Mars mission and sort through it. It's a little bit hairy to sort through, but you can see all of the NASA Mars data in one place, which is pretty cool. So we send our data to the archives. We put it up on the website. We let people download it. We have automated download capabilities too. We also sometimes write software tools that let people analyze data and grab data at the same time. And so this is a tool that we wrote for Maven that lets scientists not just look, not just search for data, but actually display it in 3D in this case, because 3D is pretty and we like to look at it. And so you can see that it's giving you a lot of detail about the location and time and season and distance, all of that information about when and how the data was collected. And oh, there's our little spacecraft. So you can see where the spacecraft was and see some information about, see some real data that was collected, and then manipulate that data and work with it, and not just view it on a website or something like that. So we create these tools to make it easier for people to download and work with the data. And that's another way we do data distribution. And then one last fun way that we distribute data is that we like to make these fancy visualization tools. And this is fun, right? So I showed this, this was at the beginning of the presentation. And I'm going to quit out of my slides and see if I can switch over to my browser. Here we go. So this is something fun that we do. Let's go. Let's see if Maven, oh, there it goes. All right, so we take Maven and we have Maven data, and we can overlay the data on the track of the spacecraft here. You can't see, you can see my mouse. You can see this is an argon density measured, whoosh, there it goes, measured by Maven at Mars. And so we like to be able to look at this in 3D over the surface of the planet, and then you can sort of pause and rotate it around. And I mean, honestly, this just looks cool. This is really fun to look at. But we also do it because we think it's really useful to be able to view more than one data set in 3D on the planet and say, what was going on here? It helps you figure out what was going on with the data at any given time. We've done the same thing for MMS. So you can sort of see the spacecraft zooming by. And we're still working on this. This has actually been updated recently, but we haven't quite released it yet. But we think it's going to be useful for people to be able to view the spacecraft, or all 4 of the spacecraft, and see how they orbit the Earth, see how they behave, and see what the data looks like from that spacecraft in 3D. And so we love building tools like this. We love Tom's team that helps us build tools like this, which is really great. And this is just yet another way that we get the data out there in front of people and make it more interesting and more comprehensible for everyone. And so that concludes my presentation with that, with the pretty pictures, of course, is where we want to end. Thank you all for listening. I hope that I have presented something that you've learned a little bit about data processing and the way we handle data here at LASP. And I would be happy to answer any questions if you have questions. Thanks very much. Steve.
Those NASA websites that you showed just a moment ago,
yeah.
Literally anyone can go there and get data from them? You don't have to have a login and a password or pay money or anything
Nope.
like that?
They are free and open. Yep, they're pretty dense. There's a lot of data there to plow through, but yeah, they're free.
Consider them prepaid.
That's right. Yes, a microscopic fraction of your tax dollars goes to that. Lisa, yeah.
I was just this great talk, super interesting.
Thanks.
And I was curious about, you mentioned about the artifacts and, it looked like a little wrinkle to me on that picture.
Yeah.
I mean, there's a history of sometimes like what data from like space, I'm thinking of the ozone story where like a bunch of data were kicked out, early on in the process that turned out to be the ozone hole, but like the algorithm, didn't realize that it was actually the real data. Are there any examples from these kinds of like space, planetary explorations where that's happened, where the correction turned out to be like, oh, that was real?
Yeah, gosh, off the top of my head, I'm not sure, but yes, I'm sure there have been. And this is something, this is why we talk about data provenance and keeping track of how this data processing happens. And so one thing I didn't say is that all of those processing levels, the software that we use to do that processing, there's a real movement toward providing that processing software alongside the data so that anyone can see how you got from level 1 to level 2, because that's really important. And other scientists are going to want to review that and say, hey, did you know that when you did that step, actually you had a minus sign missing in there and there's a problem? And so that's something that people are starting to do a lot more of now, is document which version of the software was used to do the processing and release the software into the public domain and so on. Yeah.
You mentioned that some of your data went to Google Mars.
Yeah.
How do you decide what data goes to either Google Sky or Google Earth?
So actually, you don't have to send it to them. You can just, how did we do this? You can put your data into a format that you can then release as a KMZ file or something, a file that is interpretable. And then anybody can load up Google Earth, Google Mars, and you load it on your own computer, and then you download a file and say, hey, Google, I want to plug in this file that I just downloaded. So it's more like, opening a file with an application. You don't have to send it to Google. Yeah.
You mentioned that you had to schedule time with the Deep Space Network for various satellite data. As we get more and more satellites up there, are we running out of bandwidth to get as much data from them?
Yeah, we are. It is a concern that the Deep Space Network is very tightly scheduled, is perhaps overscheduled. There are other networks and other receivers available. ESA, the European Space Agency, has its own network as well. It doesn't have quite as good complete coverage of the entire Earth as the DSN, so the DSN is still a favorite in some ways. Other countries are also building their own receivers. India has its own antenna for listening to its spacecraft. So there is some work being put into it. Also, the DSN is being refurbished. They're doing, constant upgrades on their antennas, I believe, so that they can keep operating all of their antennas and get more data back. But yeah, it's a known problem. I don't honestly know what the solution is. That is NASA's problem and not mine, thank goodness. Chris, do you know anything about that? Anybody else want to contribute? Yeah.
Isn't it the case that MMS sends down so much data that we overfill the bandwidth, and you have to make choices about what we're going to send down?
Yes. Yeah, so I didn't go into this, but some spacecraft, like the ones that are at Mars, only send back a little bit of data because it takes too much power to send that much data back from Mars. But spacecraft that are closer to home can send back enormous amounts of data, and in fact, it can be too much to handle. And so our solar observatories and MMS have vast amounts of data coming back. And so what we do is we often, with some of these cases, we'll downlink a sort of low resolution version and look at that first and say, ooh, something really interesting happened on May 23rd. I want to get more of that data at a higher resolution. And so that's an ongoing process as you get the low resolution data, and either a real person looks at it or a computer looks at it and identifies the places where you want to be downloading the higher resolution data from.
One way DSN handles this is through careful scheduling. They start scheduling the resources 6 months in advance, so visions submit. The schedule kind of one, DSN starts, so you can fit the schedule in advance. But they're also working on technological improvements too. I think back to that slide I showed that the DSN is a little waveforms and so forth. Some of the antennas were actually communicating with multiple spacecraft simultaneously. So they're pretty technology independent. So the beam or the area that the antenna can actually see, if there are multiple spacecraft present, you can all of them at the same time. So they're not simultaneous.
More questions? All right. Thank you all very much for coming.